Bismillahirrahmanirrahim. Assalamu alaikum. I welcome you all to the lecture number 13 for the course of control system. My name is Engineer Jaffar Ali and I am your instructor for this course. In the last class, we discussed about the RH criteria, that how you can find the stability of a system using RH criteria, and you can find or you can determine the value of the gain that should be there, that should be probable, that should be appropriate value for K, that gain that makes the system stable. And we have done several examples on the previous lecture about this RH criteria. We also discussed two of the these cases for this RH criteria, in which the first case was when the first column or the first element of the column or the row becomes 0, and in the second case was all the terms or the elements in the rows becomes equal to 0. So there were two cases in that class, and this was all about the stability of this checking the stability of a system of a characteristic equation using a RH criteria. Now in today's class we are going towards the steady state errors that are involved in this control system, this that makes the system's value unstable. So this will be our this is actually chapter number 7 from your book. If you follow the normalized book, it is chapter number 7 in that book. And to keep that in mind, it is mentioned the sections is being mentioned over here. So in the end of this lecture, inshallah, at this chapter actually, you are going to have a clear idea about the steady state error, that how you can find the steady state error of a unity feedback system. The feedback system that has a unity feedback is basically known as a unity feedback system, and how you can find the value of the steady state error for that system. You can also find a method, or you can also find the performance of that system using this steady state error. You can basically design the gain of a closed loop system to meet that ESS specification. So this is not maybe it won't be a part of your course, but just to have a clear roadmap, I've mentioned it over here. And you can also find the steady state error for disturbance inputs, and later on we will be discussing about the later part of the section, inshallah, we will be discussing about the steady state error for non-unity feedback systems. In this we will start with the unity feedback system, and later on we will hit on our next target, that is to find the steady state error for the non-unity feedback system. Later on we will discuss about the steady state error sensitivity to the parameter changes, how this steady state error is being changed when you basically change the some of the parameters. And in the last of this chapter we will be discussing that how you can find the value of this steady state error for the system represented in the state space. So this is the roadmap of this whole chapter, but we will be focusing on a few of the most of these, actually not few, most of these topics. So the first thing that is basically let's talk about a brief idea. In the previous whole course we discussed about we saw that the control system analysis and design focus on three specifications. The first one was transient response, and we did it in the midterm actually. And in the second part of the lecture we basically establish a method to find the stability of any characteristic equation using the RH criteria. There are many more methods, and we will be discussing that methods as well in the end of this course, inshallah, or including this course. And in this chapter, this is the chapter that we are actually on. Now we are ready to examine how you can find the steady state errors, and we will define different errors and derive methods to controlling these errors, because you know that if you have a good idea about the errors, you can actually have a good control over them. So you have to find the errors and then you have to negate them. So this is our main target, and we will be hitting that target inshallah in this class. So now let's talk about some of the definitions and the test inputs that will be used to check this the errors mechanism, that how you can find the steady state error. So the first thing that you need to have an idea about is basically what is the steady state error. So the steady state error is the difference in the value between the input and the output for a prescribed or prescribed test input. You know about the input. Prescribed means we already know about the test input, and there are several test inputs that we already discussed in the previous lectures. Actually, the first one is basically step, ramp, parabola, and there are many modes, impulse function. There are many modes. I think I've already taught you 6 to 7 test inputs, but we are keeping ourselves, limiting ourselves to these 3 input because these are more than efficient if you want to have a clear idea about any of the system. So these are more than efficient. So what is steady state error? So this is the difference between the input and the output of a prescribed, means you have an idea about the output, and if you get the actual output and you take your actual output to the already known output and you basically compare them, so the difference is basically known as the steady state error. And this test inputs will be used for steady state analysis, error analysis, and designed are basically summarized in the table below. So you can see that you know about this waveform. This is basically a step waveform, and this basically shows a constant position, and the time function is 1, and the Laplace transformation of this is 1 over s. Similarly, this is, you can see that this is a constant velocity, or you can say a ramp function, or its physical interpretation is basically constant velocity. The time function will be t, and this is 1 over s square. You know that if you convert this t into Laplace domain, you get 1 over s square. Similarly, this is basically constant acceleration. This is basically a parabolic function, and this diagram I'm talking about, this is basically a parabolic expression or shape, and the physical interpretation for this is basically constant acceleration, and you know that this is involves half t square. T square means this will be s3 over here. So this is the Laplace transformation. This is a good table, that is why it is mentioned over here. Let's talk about the application to a stable systems. So we know that we are concerned with the difference between the input and the output of a feedback control system after the steady state error has been reached. So our discussion is limited to a stable system where the natural response approaches to 0 as t basically goes to infinity. So we will be limiting ourselves to a stable system. We won't be going to unstable system, because if you remove the error of an unstable system, it won't be helping you anyway. If the system is unstable, it doesn't matter if you remove the error as much as you want, because the system is going to be unstable in the future. So we will be limiting ourselves to the stable systems. So keep that in mind. Unstable systems represent loss of control in steady state and are not acceptable for use at all. We already mentioned that an engineer must check the system for stability while performing the steady state error analysis and design. So this is not the part of your job, it will be a part of the engineer's job. As a technologist, I will recommend you to keep a brief idea about the engineer's job as well. That is why I have mentioned this over here, but this is not, I repeat, this is not will be a part of your job if you are claiming to be a technologist. So but to be a good technologist, you have to have a broad idea, and that includes the design engineer as well. So that is why I will be giving you some tips and clues that how you can counter that as well. So the first thing in steady state error is for the unit step input. So you know that the unit step input is basically your straight line, that is 1. This is your straight line, this is your unit step function, and if your output is something like this blue line, so you see that there is quite a overshoot over here, there is a quite a delay time over here, there is a rise time over here, there is a peak time over here, there is a settling time over here. These are all transient analysis. So the thing that we are interested in is basically this y of ss. This y of s is basically is the difference in the value, and this is 1 minus this y of s gives us the steady state error. So basically we are interested in this, the difference in the value, that how much is this y of ss. So steady state error for the unity feedback system can be calculated for a system's closed loop transfer function. You already know about the closed loop transfer function. The open loop transfer function, you can also use that. G of s can also be used to find that steady state error. You can see that. Let me describe it to you. This is the derivation. In this derivation, you can see that. Let's talk about this example, this figure A, and this figure A includes this T of s, and there is not feedback system. This is basically this E of s will be the summation of this R of s with minus C of s. So the R of s minus C of s will give you the error function, or you can say the error signal. And you see that this C of s is nothing but this T of s into R of s. So if you replace this C of s with this R of s and T of s in this function, you will get the value of E of s is equal to R of s 1 minus this T of s. Now if you apply this FVT or final value theorem and apply, and this means that you have to take the limits up to infinity. So if you include that as well, you will be getting this equation. So E of s will be converted into this e into infinity, and this will be, if you take the final value theorem, you have to move back into the time domain, and this time will be going towards infinity, and in the frequency domain it will be going towards 0. So this is the combination, and the value, basically the final value theorem states that you have to take the limits and multiply it with the derivative, or you can say s. So this is the s over here. You can see that this is the formula, s into E of s. Now if you put the value of this E of s that you just found out over here, you have to put this value of E of s into this place, this E of s, and you will be getting this value. Limit s tends to infinity, s, the same s will be coming over here, and this R of s 1 minus T of s will be over here. This whole thing will be coming over here. So this is your equation for the final steady state error. So let's talk about a quick example. This example is also from the book, and it is on the page 345, and the example is basically 7.1, and we have to find the steady state error for this T of s. T of s is mentioned over here, and the input is basically unit step. It means the Laplace will be 1 over s. So you know the formula. E of s is basically R of s 1 minus T of s that we just learned in the previous slide. If you put this values, this R of s will be equal to 1 over s, and this T of s will be this thing. So if you put this equation in this thing, you will be getting this value. You got this value. This is your E of s, and if you find this E of s, and so the first thing that you need to have to do is basically to find the stability of the system, and for that you need to basically have this equation. You will find the stability of the system using this equation, and if the system is stable, only then you are required to continue and find the value of the steady state error. If the system is unstable, you do not have to find the steady state error value. So let's see, and since this is a stable system, you have to find that in your exam as well. If you are asked to find a steady state error, the first thing that you need to find is basically the system stability, and I will already discussed about the system stability checking in the previous lecture. So this will be, you see that this is the proper roadmap that I'm providing to you. The first thing that you have to have clear idea is about the stability, and after that you are going towards this steady state error values. So if the system is stable, it means that there will be no roots on the right half planes. There will be no roots on the, or you can say poles on the right half plane. So you can apply final value theorem, and by applying final value theorem, the same theorem that we discussed in the previous slide, this theorem, you have to apply this theorem over here, and you will be getting the value of this E infinity, and it will comes out to be 1 by 2, that is half, that is 0.5. So let's talk about this steady state error in terms of this G of s, or means the forward path gain. If you are having only this forward path gain G of s, and someone asks you to find the value of this this steady state error. So you see that this is your for specifically for unity feedback system. You always keep in mind that this is basically unity feedback system. So you know that in unity feedback system, E of S will be nothing but the difference between the C of S and this R of S. So R of S minus C of S will give you the error signal, and this E of S it's the C of S is nothing but the combination of this G of S into E of S. So this is mentioned over here. Now if you put the value of this C of S into this term, you will get this equation as well. So the value of this E of S will be R divided by 1 plus G of S. So if you have the value of the given input and you have the value of the output, you can get the steady state error. And if you want to apply the final value theorem, you can also do that as well. So same thing will apply, that this S will basically goes to infinity, and in the time domain, so it will be in the time domain. So in the S domain, this will becomes to limit approach to 0, and you have to put an extra S over here, and R of S, the same thing will remain as it is. So the test signals is basically, we see that it all depends upon the test inputs that, or test signals that you give. So if the is a step function, you will be giving S. If it is a parabolic function, it will be coming. You see that if I put this R of S is equal to 1, so this S will be gone. So if I put this R of S as 1 over S, this S will be cancelled with this S. So this will be only 1 in the numerator. Similarly, if there is if you put R of S as 1 over S square, because you know if you put ramp function, so this S will be cancelled with 1 of the S, and 1 of the S will be coming in the denominator. You see that there will be 1 S in the denominator as well. Similarly, if you put parabolic input, so you know that the Laplace transformation of that parabolic is nothing but 1 over S cube. So if you put this R of S as 1 over S cube, this 1S will be cancelled with that 1S, and there will be 2S remaining, so S square will be remained. So if you apply this limits, as this S square will be 0, and you will be only remained with 1 over S square into G of S. So this is the final equation. So by using these equations, you can also find the values of the steady state error. So let's do a practical quick example. For example, let's say this is example from your book, and we have to find the steady state error for the inputs of 5t and 5t square. So you see that there are actually 3 types of function. The first one is step function, the second one is ramp function, because you see that this t is multiplied over here, and the third one is the parabolic function. You can see that t square is multiplied over here. So the function for the unit step will be the figure is shown over here. So this 120 into S plus 2, S plus 3, S plus 4, this is your E of S, this is your R of S. So the first thing will be, we have to put this R of S equal to 1 over S, and this is 5 basically, so 5 over S will be coming as this R of S, not 1 over S. This will be 5 of S, because this is mentioned 5 ut. So if you put this 5 as in the numerator, you see that this 5 over S, and this S will be 1S will be cancelled with the X in the S in the numerator in the previous slides. So this will be 5 divided by 1 plus this thing's limits to 0, and 5 divided by 1, and if you put this G of S, you see that this G of S is nothing but this thing. If you put S is equal to 0, so 0, this will becomes 240, and it will be divided by 4 3s are 12. So if you do this kind of, so you will be getting 20. So the G becomes 20 by putting S0, because you know that the limits are applied to 0. So this G become 20. So the whole steady state error will be coming out 5 by 21. Similarly, if you put this equation, that is 5t, it means there will be 5 over S, because the equation was S r of s and 1 plus g of s limits to 0. This was the actual formula, limit s tends to 0. So if you put r of s equal to 5 over s square, so 1s will be cancelled with the square and only 1s will be remain in the denominator. Now if you apply this limit over here, this whole thing will become 0 because this s is multiplied over here. So 5 by 0 means infinity. So there will be a huge error if you apply this as a test input. Similarly, if you apply this thing as well, 5t square, it means this will be 10 by s square, because this was, you can see that this was 2 actually. You see that this is 2. So that is why 10 by s square into g of s, and this will also as this thing approaches to 0, this whole term will be 0 and the overall term will be infinity. So the overall error for the parabolic function will also be infinity. So this is the last example for today's this part, actually the first part of this lecture. In this part we have to find the steady state errors for the inputs of 5t, similarly 5u of t, 5t and 5t square for the system, and the function u of t is a unit step. It is mentioned that this is unit step function, and the first thing that we always have to find is this to check whether the system is stable or not. So it is also mentioned over here, the first thing that you have to verify is that the closed loop system is indeed stable. So if it is stable, then you have to move forward, and if you do the same thing, if you put this 5 over here, 5 actually represents a numerator, and if you apply this as limits approaches to 0, this g of s will become infinity. How? Let's see. If you put this 5 s is equal to 0, this thing 0, so the numerator will become so you see, if you put the value of s equals to 0, these terms will be becoming 0, and this thing, this s will also be 0. So it means anything divided by 0 becomes infinity. So the gain will be infinity. You see that this gain is basically going towards infinity. Now if you put the gain to infinity, and anything divided by this gain infinity is basically 0. So anything divided by this infinity is 0. So the error, steady state error for such kind of input is basically 0. There will be no steady state error. Similarly, if you put the value of this 5t, it means this is 5s, 5 over s. And if you see that if you put before applying this thing on this g of s, if you put this value s is equal to 0, this s and this s, there is one s over here, and there is 1 over s in the g of s. You see that there is 1 s in the g of s. This is the same s. So this s and this s will be cancelled out, and you will be only remaining with this g of s. And if you put the value of this s is equal to 0, let me clear it for you. So if you put the value, this s will be cancelled out to the same as in the formula. So ignore this s, and if you put this s is equal to 0, 0, 0, 0 and 0. So in the denominator there will be 12, and numerator will be 12 and 200. So this 12 will be cancelled out with this 12, and you will be only remain with the 100. So you will be remaining with the 100 in the denominator. You see that this will be denominator as 100, and 1 over 100 will give you 1 over 20. 5 over 100 will give you 1 over 20. So that there will be this much error if you apply such input. And the last thing, this is basically, you see that there will be there are 2s in the denominator. That is why it is also going towards 0, because there will be 1s in the denominator, and 1s will be cancelled out because of these g of s, but there will be 1s over here. So this s will be causing this whole thing going towards 0, and anything divided by 0 makes the system or the equation towards infinity. So the system or this equation will tends towards infinity. So the parabolic error for this function is basically infinity. So this was the first part. I hope that you have learned quite a lot. Keep practice these kind of questions, because this course is basically the requirement of this course is more practice. I have already discussed it with you in the previous lectures. So also note down some of the questions that you face, or any confusions or queries. Write it down with yourself on the white paper, so that in the class you are able to ask that questions, because you know that the more you ask, the more you learn. Thank you very much. I'll see you in the second part. Allah Hafiz.